Hi. In today's video, we're going to talk about a really interesting reaction called ozonolysis. So ozonolysis, as the name might tell you, it has ozone in it. So this is the same thing that's found in the atmosphere, that we talk about having an ozone layer, and ozonolysis can absolutely happen on real alkenes that are floating around us at any given time. So when ozone reacts with an alkene, what it does is it breaks that double bond, and it gives you two new molecules, so it breaks the molecule in half. So the way to think about it is to recognize that the oxygen atoms of your products, in this case a ketone and an aldehyde, came from the oxygen atoms that were part of ozone. And I often recommend drawing a line through an alkene and keeping in mind that you've kind of cut that bond in half, kind of like with scissors. So let's look at the mechanism of how that works. So if you have an alkene, in this case there are two methyl groups and a methyl and a hydrogen atom, and the ozone, so this is the structure of ozone, a cycle addition occurs, similar to what you've seen in the previous mechanism with osmium tetroxide. So cycle additions are kind of a common theme we're seeing here with double bonds or with alkenes. So you form this five-membered ring that has three oxygens that are all right next to each other. So these bonds are actually quite weak because these oxygen-oxygen bonds are all actually quite prone to reaction, as we've talked about before. And what happens is that this molecule undergoes a retro cycle addition. That is, it breaks itself apart, but not in the same way that it formed. So this carbon-carbon bond has now been broken to form a double bond between this carbon atom and this oxygen atom. I've now highlighted the oxygen atoms in different colors so we can keep track of these atoms as they go along. Notice also that I have rotated this acetone molecule from the original orientation that was shown here. So now you have a carbonyl, a ketone carbonyl, and you have this other carbonyl which has kind of a bonus oxygen attached to it. This oxygen has a formal negative charge and is nucleophilic. And this carbon is electropositive relatively. So again, you have a nucleophile and you have an electrophile. And so another cycle addition occurs to give you now this key intermediate. So this compound up here is not stable, but this ozonoid down here is relatively stable. This reaction is actually quite fun to do because ozone, when it's dissolved in solvents, has this beautiful blue color. And as it reacts with the alkene, the blue color dissipates. And that's how you can tell that the reaction is occurring and going to completion. So now we have this ozonoid, and now once we know that part of the reaction is complete, we go ahead and add our second reagent, in this case DMS, dimethyl sulfide. What dimethyl sulfide does is a sulfur interacts with this oxygen, in this case this black one. It could also interact with the blue one, they're the same, but for the sake of this mechanism I'm showing it with the black one. And this breaks this weakened oxygen-oxygen bond. Again, remember, when there are two hetero atoms that are bound together, it's a weakened bond. This gives you an oxygen with a negative charge, and now this sulfur way over here with a positive charge. If we now complete the mechanism, you see that through all this bond breaking, this is good to practice to see if you can pause this and draw these electron flow over here and see if you come up with these three products as your end result. You see that one of the oxygen atoms from the original ozone winds up on the aldehyde. One of them winds up on acetone, and the third oxygen of ozone, in this case, ends up bound to the sulfur, and now we've actually synthesized DMSO, the solvent that we've used many times before. So again, I'll highlight here that here we had this ketone and aldehyde, and here again we have a ketone and aldehyde. I'll note that this can also occur in a situation where you'd form two aldehydes or a situation where you'd form two ketones. So let's look at some syntheses where this could be involved. So if you were to see a reaction like this, you see ozone and you see this alkene. The way to think about how to do this is you draw a line through the middle and you want to make sure you count your carbons. That's a really common error, to not count your carbons. So again, we drew the line down the middle and we counted our carbon atoms. And on one side we have 1, 2, 3, 4, 5 carbon atoms. And at carbon 4, you can see that that's where the double bond was, and that's now where the double bond to oxygen is. And the other side, you had 1, 1, 2, and the new carbon-oxygen double bond is at the on the 2 carbon. So let's look at the other way around, where you have now these 2 aldehyde products, and in this case these 2 aldehydes are actually the same aldehyde, so that means that the molecule we started with was was symmetrical. And we have, again, ozone as our reagent, so we know that this must have come from a cleaved double bond. And now we can count our carbons to make sure that we have enough carbons in our product. So we have 1, 2, 3, 4, and then 1, 2, 3, 4, and we find in the middle that this is where the double bond must have existed. Right now I've drawn this as the more stable trans product, or E product, but it could have also been the Z alkene. There's no way of knowing based on your products if you started with an E or a Z alkene, because that information has been lost when the molecule was cleaved. Finally, another version that you might see is a cyclic alkene, and what happens with ozonolysis in this case. So again, we will draw a line through that alkene and count our carbons. So in this case, we have a 5-membered ring, so we have 5 carbon atoms here. Bound to carbon 1, there will be an oxygen, because again, that's where this double bond to the alkene was, and so that's now where the double bond to the oxygen is going to be. Similarly, at carbon 5, there's also going to be a double bond to an oxygen. But there's one last thing we have to keep track of. This starting molecule had 6 carbon atoms, and so that 6th carbon atom was bound to the 5, and so we go ahead and draw that in. So we end up with this linear aldehyde ketone that came from this cyclic alkene. Thank you for your time, and I look forward to any questions that you might have.